This is Lab 1, Constant Velocity for Physics 2211. So the purpose of this lab is to predict the future position of an object moving at constant velocity using Newton's second law. So in this lab, I will be testing Newton's second law of motion / the momentum principle by observing a soccer ball moving at constant velocity. I compared data from an observed model to a computational model to see how well my object obeys the momentum principle. So Newton's second law states that force is equal to mass times acceleration. And I also use this formula which states that final velocity is equal to initial velocity plus net force divided by mass times delta t. And so the momentum principle states that the change in momentum of a system is equal to the net force times the duration of the interaction. In this experiment, the momentum principle is used to predict the future behavior of an object in constant motion. And so to predict the object's future motion, I used a computational method to apply the principle of momentum. I find the initial conditions such as velocity, time, and position of my object, and then use a small delta t. In this case, the net force is equal to 0, and because of that, Newton's first law is also observed in this model, which states that an object in motion will stay in constant motion unless acted upon by a net force. And also, some assumptions that I was able to make in this model were that my soccer ball was rolling on a smooth, frictionless surface, and I was also able to assume that the net force is equal to 0. And so this is my model that I used in Tracker in order to observe Newton's second law. So for my experiment, I used a video of a soccer ball rolling on the floor at constant velocity, and I used Tracker to analyze the motion of the ball rolling across the floor. And so this is a clip of the soccer ball. So the clip begins after the initial kick of the ball when it begins to move at constant velocity. The first frame was used to set the origin of the system at the center of the ball. The positive x-axis is set to the right in the direction of the ball's motion, and I calculate the position of the ball by tracking the point mass using the center of the ball. I then use the data that I got from Tracker to create a computational model. So this is just a closer look at the graph and the table that I got from Tracker. And using the values from this table, I was able to calculate some of my initial conditions. So using the table, I got my initial position as well as a second position in order to calculate my initial velocity. As you can see on the slide, I use the formula velocity equals change in position over change in time, and I was able to calculate my initial velocity as 0.963 meters per second in the x direction. And this is the code that I use in GlowScript in order to model my ball's position. So I only had to input the initial conditions that I got in the last slide, as well as changing the net force, which we assumed to be 0 based on Newton's second law, and then also changing the object's velocity using the momentum principle. And so this is the graph of my data. As you can see, the red is equal to the predicted position I got from my computational model, where the blue is equal to the observed position. And so as you can see, they are pretty close to one another. At about 0.5 seconds, the model graph increases faster than the observed graph. And this is showing that the model predicted that the ball would travel further than it did. This shows that there was some outside forces acting on the ball because the observed motion, was not as perfectly constant as the model predicted it would be. And so this is showing that there are forces acting on the ball, which is why it did not have the same perfect constant velocity. In conclusion, the what if question: if I were to flip the orientation of the axes, there would be a change in the direction of the motion. However, the magnitude of the positions would be the same, but the direction would be in the negative x direction rather than the positive x, and my graph would have a negative slope. And so, answering the what does it mean question, it is not possible to say exactly how many pushes or pulls are added together. It is only possible to know that the sum of the magnitudes of each of these forces will add up to 0.